You ever wonder how your inbox just knows that an email is junk? I mean, it's not magic, and it's definitely not some giant simple list of forbidden words. Nope, it's all about probability, and it's powered by a really elegant algorithm called naive Bayes. Today, we're going to build a spam filter right from scratch and see exactly how this thing works.
I mean, think about it. It's a tricky problem, right? An email offering you free money gets zapped into the junk folder instantly. But a message from your friend saying, "Hey, I'm free on Friday," lands safely in your inbox. The filter seems to get the context, but how? Well, the secret isn't about blocking single words. It's about understanding the likelihood of words showing up together. The answer, my friends, is all about probability.
So, here's how we're going to break it all down. First, we'll get into the core idea, using probability to classify text. Then, we're going to dive into the math that makes it all tick, Bayes' theorem. After that, we'll uncover the clever, kind of sneaky shortcut that makes this whole thing so fast, the naive part. And finally, we'll put it all together and build our filter.
Okay, so the old school way of catching spam was just to have a huge list of bad words. But, spammers get creative. A modern filter has to be smarter. It has to learn. So the big idea is to stop making these rigid rules and start calculating probabilities instead. We just need to figure out how likely it is that certain words will pop up in spam versus in your normal everyday emails.
And this is where that learning happens. We feed our algorithm what's called a training set. It's just a huge collection of emails that we've already labeled. Thousands marked as spam and thousands marked as ham, which, by the way, is the charming industry term for the good stuff, the non-spam. From all this data, the algorithm starts calculating how often every single word appears in both of those categories.
So that's a great start, but how do we actually turn all those word counts into a real prediction for a new email that just arrived? How do we formalize all this? Well, this is where a brilliant piece of math from the 18th century comes into play, and it is the absolute heart of our filter.
And this is it, Bayes' theorem. Now, it might look a little intimidating, but the idea behind it is incredibly powerful. What we really want to find is P of S given W. In plain English, that's the probability that a message is spam given that it contains certain words. The theorem is basically a recipe that shows us how to calculate this by using probabilities we can easily figure out from our training data.
Let's just break it down real quick. PS is what's called the prior probability. It's basically asking, out of all the emails in the world, what percentage is spam? Easy enough. PWS is the really key piece we learned from our training data. What's the probability a known spam message contains a word like, say, Viagra? And finally, PW is just the overall chance that word appears in any email, spam or not. Bayes' theorem lets us stitch these three simple pieces together to get the answer we actually care about.
Okay, this all makes perfect sense if you're just looking at a single word. But emails have tons of words, right? Hundreds sometimes. Trying to calculate the probability of every possible combination of all those words appearing together? No way. That's computationally insane. The model needs a shortcut. It needs to simplify the problem, like a lot.
And here is that beautiful shortcut. The naive in naive Bayes comes from one great, big, and really useful assumption. We just pretend every single word is independent of every other word. We completely ignore context, grammar, all of it. So to get the final spam score for an email, we just calculate the individual spam probability for each word and multiply them all together. Now, a little pro tip, multiplying lots of tiny fractions can cause issues for computers. So in the real world, what we actually do is add the logarithms of the probabilities. It's a clever math trick that gets you the same ranking, just much more reliably.
And this is the main takeaway here. That assumption, it isn't a flaw. It's the whole reason this algorithm works so well in the real world. By making the problem simpler, it becomes incredibly fast, it doesn't need a mountain of training data, and it's surprisingly effective. It's the perfect example of a good enough model being way more useful than a perfect one that's too slow to actually run.
Okay, our model is fast, it's clever, but it does have a potential Achilles heel. What happens when it sees a word it's never encountered before in a particular category? Like, what if the word meeting shows up in a new email, but in our entire training set, that word only ever appeared in our ham, our good emails?
This is a huge problem, a catastrophic one actually. If the probability of the word meeting in a spam message is calculated as 0, our whole multiplication just collapses. It doesn't matter if the email also has a dozen spammy words like invoice or winner. That one single zero will force the final spam probability for the entire message to become 0. Our model would be completely broken by just one new word.
Luckily, the fix is super simple and honestly pretty elegant. It's a technique called smoothing. We basically give every single word in our vocabulary a tiny head start by adding what's called a pseudo count, let's just say the number 1, to every word's frequency count. We guarantee that no word ever has a 0 probability. It might be a very, very, very small probability, but it's not 0. And that simple trick makes our entire model robust.
All right, our toolkit is complete. We've got Bayes' theorem for our engine, we've got the naive assumption for speed, and we've got smoothing to make it robust. It is time to put our shiny new filter to the test.
So here's the game plan. We train our model on one big batch of emails, letting it learn all those word probabilities for both spam and ham. Then, and this is the important part, we unleash it on a completely separate set of emails it has never ever seen before to see how well it does. This is the true test for any machine learning model.
And here are the results, laid out in what's called a confusion matrix. Let's walk through this. Up in the top left, we've got 101 true positives. These are real spam emails that are filter correctly flagged. Awesome. Bottom right, 704 true negatives. These are good emails that we correctly let through. Also awesome. But we also made some mistakes. We have 38 false negatives, that's spam that we missed, and 33 false positives. Those are legitimate emails we accidentally called spam. Oops.
So how do we actually grade this performance? Well, let's start with a really important one. Those legitimate emails we accidentally flagged as junk.
This brings us to a metric called precision. It asks a very specific question. Of all the emails we predicted were spam, what percentage were actually spam? So we take the 101 we got right, and we divide it by the total number we flagged as spam, which is that 101 plus the 33 we got wrong, and that gives us a precision of 75%.
Okay, but that's only half the story. What about all the spam that slipped through the cracks and actually landed in the inbox? That's a different question.
And for that, we use a metric called recall. This answers the question of all the spam that was actually out there, what percentage did we manage to catch? So for this, we take our 101 correct guesses and we divide by the total number of real spam messages, that's the 101 we caught plus the 38 that we missed. And this gives us a recall of 73%.
So a precision of 75% and a recall of 73%. You know, when you step back and think about it, that's incredibly effective for a model that's built on one fundamentally wrong assumption and a couple of clever math tricks. It's a fantastic testament to the power of smart simplification.
And that really leaves us with one final thought. The naive Bayes classifier works so well because it makes this big, simplifying assumption that's just good enough for the real world. So the question to you is, what other naive but incredibly powerful assumptions are hiding inside the technology you use every single day?
And that's our deep dive into naive Bayes. If you enjoyed making a complex topic simple, make sure to subscribe for more explainers that get right to the point. Thanks for tuning in.